a relation. Okay, a relation up here is our quick definition of it. A relation, as you guys can definitely read, but a relation is just like anything you guys really been doing. A relation can be just an ordered pair, okay, a point, a series of points there. In that relation, we know can make a type of graph, and it could be a relation can be coming from a word problem, it can be coming from an equation, it can be coming from all different sorts of things. Now, in math, we care when that relation becomes more of what we say is a function. So when does a relation, a specific type of graph, a specific type of equation, a specific type of word problem, when does that specific relation become what we call as a function? And that's what we're going to try to see here today is when do relations become functions? And then after that, what type of functions are out there? And we're going to see the different types of families that are out there for our types of functions in algebra 1. All right, James, you're in enough trouble today. Okay, in functions from our algebra 1 families, and then as you're going to roll into algebra 2, you're going to add more families onto that. Okay, just throw it right there, Patrick. Thank you. Okay, so let's see when does a relation become a function. And most of the time, it's really easy to kind of start throwing out examples. When it is a function, when it's not, and that's usually kind of where you build to see, oh, this is when a relation is a function, and when it's not. Not really when it's, I can throw out the definition here. I've thrown out the definition here. It's kind of maybe just like word salad, all right? But let's look at some examples of when it is and when it is not a function. And ideally, you've seen this before from your 7th and 8th grade teachers, and it rings a bell, but if not, okay, let's talk. I've got myself 2 tables. I've got 2 relations here. Again, just a series of ordered pairs. Okay, a bunch of ordered pairs here. This table is saying this relation is considered to be a function, and this table is considered to be not a function. And as we look at these ordered pairs in both of these, can anybody give me a quick explanation of why this one is considered to be a function and what in here is maybe saying this relation is not making it a function? Jillian? On this one right here, she's saying there's 2 the same values in x right here, 3. Okay, I've got that 3 being repeated, don't I? 3 is got an input. Okay, remember, this is our x's. This is what we call our inputs. We call those, again, inputs, or we could also call that our domain. We have repetition, okay? We have 3, but we look at the output. We look at the range. 3 is going to where? 4, and it's also going to where? 7. That cannot happen to be considered a function. You have an input of 3, and what do you get for an output? 4 and also 7. You can't have the same input going to 2 different outputs. That's where that screws it up. 3 can only go to 4, that's it. Or 3 can only go to 7, and that's it. You can't put an input in and get 2 different outputs. That's where that thing is screwing it up. So on that first one, we don't have anything repeated, do we? Okay, and that's where we're saying this relation is cool. That's okay. That's to be considered to be a function. But that's where, as Jillian pointed out, this is where we're saying it's not a function. Okay, so this is an example where seeing where it works and where it doesn't work. Okay, so as we work through here, okay, we're going to kind of jump around. We got a graph. Okay, graph table values, one and the same. The only difference is on a graph, we took those points and actually graphed them out. So off this graph, if we were to take these points, here's a nice point. Where's this nice point located at? This point is located at 0, 0, right? If we got another nice point where, looks like right here at where? 1, 3. Another nice point up here, which is where? 2, 4. Another nice point where? 3, 3 looks like. Another nice point where? Yep, 4, 0. If I continue to do this, and at any point when I did this, and I label out these into a table. Are any of my x's repeating and give me different y values? No. And what do we then classify this as? We have ourselves a function. Now, that's annoying. I'm not going to keep labeling this out from a graph to a table values. So hopefully what rings a bell is what we call right up here the vertical line test. So if you take your pencil, place it vertically on the left side of your graph, your vertical line test does the exact same thing we just did. When you drag your pencil across this graph now from left to right, what should happen with your pencil to be considered a function is that it should only hit your pencil at that graph one point at a time. So as you drag that pencil from left to right, if it's only hitting it at one point at a time, then it is what we consider to be a function. So again, you drag it from left to right. At any time, is that hitting our graph at 2 points at a time? No, it's not. Is we can see on my pencil and your pencil it goes 1 point, 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 and forever and ever and ever. So that's another quicker way to say it's a function. We say it's the vertical line test. It's a nice visual. Now, real quick, on this one, I can list out all these points again. I could say 0, 0, 1, 1, 4, 3. Another nice point is up here at 9, 3. Okay, but those are all one input gives me one output, right? But vertical line tests, is it repeating at any time? No. So what do we have here? We get ourselves a function. Okay. Now before I do that, we talked about this graph a couple times. We're going to do it more intense work with it next week. Let's know our families. What family is this a part of? This is our quadratic family. Correct. We want to start knowing what families we're a part of. This is my quadratic family. This family, this is more of an algebra 2 family, but we do throw it into algebra 1. This dude right here, this is part of our square root. So if I typed in the square root of x, what I get in the result is that graph right there. That's the square root family. Okay, that's the square root function right there that's being displayed. So ideally, as we work through some of these over the next week and then we roll into algebra 2 next year, whenever I throw out the square root of x to you, you should know immediately what graph it is and know what that shape's going to be. All right, let's go. What do we have up top there, function or not? That's a clear one, right? It is failing all throughout here. I mean, you can pick at any time, -5, what, 3, -5, -3, right? It's screwing up all throughout there. Right here, we're at what, -2, 5, and -2, like it's screwing up all throughout. So this is not a function. Now, on here, obviously it's a circle. We are going to talk about this circle equation. It's going to have a special equation down the road. But in terms of a function, we say, well, it's not a function. It's a relation, but it's not a function. Letter D, is that a function? No. As I drag it across, it screws up all throughout, doesn't it? Like all throughout, I have 3 points lined up vertically. Anywhere you want to do it, it's just screwing up all throughout, isn't it? So this one is, again, it's a function. Sorry, it's a relation, but just not a function. Okay? All right, so take a quick sec based off what we just talked about. Create me a graph, create me a relation that is, and then create me one that is not. Whatever you want to do, just don't create me one that we just talked about. Go a little crazy on your own. Make me one that is, make me one that's not. Just don't make me one that's already been on our paper. There's more than one answer here. There's an infinite amount of possibilities there. Okay? You're doing that. Okay. Here's again an increment of possibilities you draw for that. Okay. Just peeking over some shoulders that I'm walking around here. As long as it passes that vertical line test, I see just a whole bunch of possibilities there. I saw a linear function. I saw a quadratic function. I saw, which would be considered the sine function. I saw somebody do the exponential function. I mean, I know that those are those, but those are what they are. All right, I saw somebody do what we say is the absolute value function, or not. Okay, you could just make something that is not any of those, more of a V-shaped one. Okay, some peaks there, and this is just again a function. Okay, over here, not a function. Take that quadratic and turn it on its side. Okay, turn it on its side there, and that's failing all throughout, isn't it? Okay, or you can go something else. Go with the kind of Harry Potter lightning bolt there, and it's fine, it's fine, it's fine, but right here in the middle is where it screws up, doesn't it? So those are all relations, but not a function. Which leads me to then that domain and range, and identifying all that. Okay, so it's in that domain and range where you're looking at that tells us if it's a function or not. So what we want to now do is beginning the analyzation of our graphs. And one of the very first things we always look at when we analyze it is, well, what's the domain and range? So let's talk about domain and range. And if you're sitting there going, I don't remember domain and range, okay, cool. Let's talk about it right now. First thing is, let's take those A, B's, and C's. Just tell me yes or no. Let's get the function out of the way. Yes or no. Is that a function? Yes or no. Get that out of the way. Okay? That should be 5 seconds there. 1, 2, 3, 4, 5. What do we got? Yes or no? Second one?
No.
And?
Yes.
All right. Nothing crazy there. Okay. Let's see what you guys remember or not about the domain. Let's focus on the domain first. So the domain is, hopefully you remember, the domain is, yes, the domain is the x's. It's the inputs. It's the independent values, okay? So the domain, we are always focusing on the x's, all right? So we have all these x's from negative infinity to positive infinity to choose from. Don't be greedy, all right? Let's not be greedy here. To make this specific graph right here on this one, we don't need to always use from negative infinity to positive infinity. We may not need to use all of them. So in this specific graph, we got to look here on that graph and see what is the leftmost x value and what is the rightmost x value, which brings me back into the interval notation from yesterday. Okay. So what I like to think about the domain as like a left wall and a right wall. Can I put a wall up on the left side and the right side? So on this one, what is the leftmost x value? What is its starting x value? Negative what? Negative 5. So I always ask my students, can I put a wall up? And if I can, that means where you are starting off at that specific value, which as you just said, starts off at negative 5, right? So you're looking at the x's. Got to train your eyes to focus on the net x's, and we're starting off at negative 5. Now, can I put a right wall? We go from left to right, and I'm using these x's. Then where do I stop at on the right-hand side? Right. I stop at 5. My graph clearly stops at 5. Now we bring in our parentheses and brackets from yesterday. When you said negative 5 to start off with, well, what's there? An open or a close? What do we say? parentheses, right? So don't forget about what we talked about yesterday. We're going to use our parentheses. If it was an inequality, that would go with just a less than or greater than symbol, right? At 5, you stopped at 5, you told me, which is correct. What's there at 5? Close, which implies a bracket. So that's all the x values that are needed to make that specific graph. I need -5, I need -4, 3, 2, everything between there up to 5. And that's it. I don't need to go over here to 10, do I?
No.
I just got to go right there. That's the domain values. Now I need to also choose from the y values. Now the y values, these are the ones that students struggle with most. The domain's usually fine. The range, bottoms up. Okay, you read the range from the bottom up. Because why the bottom up? Negative to positive, right? Left, negative to positive. So bottoms up. I always like to think about the range as floors and the ceiling. Left, this is the house. Walls, left and right, floors and ceilings. So, is there a floor? What's the bottommost y value here? -2. I'm going to put my floor in here. As you said, -2. And then I go up, 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 up. Can I put a ceiling in? Is it stopping where? 2. And then I come back around and I put my parentheses and brackets in. Now, down here at that floor, I've got an open, I've got a close, and I've also got this solid little piece of segment from 2 to 3. Close takes priority. Solid takes priority. So because of that, what am I going to use at -2? I'm going to use a bracket. Right. If you get something at the same level, that solid takes priority. Okay. Up there at 2, you told me to stop. I hit my head on the ceiling. That's all solid segment in there, right? Because it's all of a solid segment. That means what? Bracket. Okay, there's no openness, is there? There's no open circle or anything. It's all solid. Solid means what? Bracket. So I don't need to go up to 4 for the range, so don't get greedy. Stop right there at 2. Only take what you need. Okay. That's the domain. That's the range. That's one. Let's go with another one. Up on the next one. Domain. Let's train our eyes. Domain. X's. Left to right. Can you put a wall in there? Left and right. What's my leftmost wall? Yep, look closely. It's at -4 to start. Okay. 1, 2, 3, -4. Comma. Rightmost wall. Yeah, I'm hearing a 3. I see a 2, but that's the bottom one. But the top one stops at, as you said, 3. 2 to 3. Sorry, -4 to 3, I should say. Now, when you say -4, parentheses or bracket. Bracket, because when I look at that -4, yeah, there's no necessarily dot there, but I mean, there's a point there, isn't there? And it's a solid. It's solid there. And what does solid again imply? Bracket. If it's an open point, they would have put an open point there. Otherwise, you assume it's solid. And what did you say at 3? 3 is going to be a what? Yeah, it's clearly an open point. So there we go. All right, bottoms up. Range. Bottoms up, people. Floor is what? -5. Right. I can put a floor in at -5. Can I put a ceiling up?
Yeah.
I stop up here at 5. And then I always come back around and I put my parentheses and brackets there. What's my floor at? Parentheses. -5. What's my ceiling at? Parentheses, as you can see where it stops at 5, it's an open point. Okay. All right, let's change it up now. Those are fairly straightforward because you can see clearly points ending. Let's go do the domain here in the next one. There's a slight twist now. All right, left to right. Where's this left wall starting at? Thank you. So this one does not have a wall, does it? It looks like it's stopping at -6, but what is that actually doing here? It's pointing to the left, isn't it? So I'm going to take down my wall. There is no wall here. This graph, this is the square root function. And this square root function starts way out here in Mr. Carroll's room, no past Mr. Carroll's room, all the way out here. It starts out here at -infinity. So left to right, as you just told me, it starts way out here at -infinity. All right. Comma. Now I come back into the problem, and where do I put my right wall at? Yep, we can see it is stopping at 4. So the only thing I do have in this one is a right wall. If I don't have a wall, I don't put a wall up. And what do we have? Parentheses, brackets. Infinity, yeah. And 4 is a what? Bracket. Good. All right. Bottoms up, people. Bottoms up. Range. Do I have a floor? Where's that floor start?
0.
Starting on Y's, remember. It is at 0. Right, and that's, I heard a 4, and I totally know why we say a 4. Your eyes are drawn back to that 4, but remember, we're working on the Y's. It is at 0. And then, do we have a ceiling at 3? No, what's this arrow doing? It keeps going up. And whoops. And it keeps going up. Now I'm exaggerating it. So, where's my ceiling at? Do I have a ceiling? So where's this going to? Infinity. So I started at 0. I did have a floor. But again, do I have a ceiling? No. Which means I'm going to infinity, as you said. Okay? So from 0 to infinity is what I got. I have to use every y value above 0. No. 0, infinity. What do we have? Parentheses or brackets? Yep. Bracket gets the 0. Bracket gets the 0. And infinity gets the parenthesis, right? Alrighty. Okay. Next row. 1, 2, 3, 4, 5. Go. You haven't done so yet. Tell me, function or not? Straight across. Okay. Do we have a function there or not? Make it quick. All right, that was more than enough. Quick yes or no. Function. That's a yes. Function. Function. No. Alrighty. Let's do it. Domain and range. This one gets a little funky again. Okay, left to right. All right, domain, left to right. Can I put a wall up?
Nope.
Now, again, it looks like there could be a wall as it stops maybe here at -5. But I'm going to tear down this wall because this arrow, it is opening down. I don't care about down because domain is left to right. What I care about this, I'm going to exaggerate it. This thing is opening to the left. And it's still opening to the left forever and ever and ever. So this thing, again, is starting way out here. Where? Yeah, this thing is starting way out here at -infinity. So, yes, I care. Your eyes are going to be drawn down. Naturally, they are. But you got to remember, domain is left-right. That's why I like to talk about walls. Left-right wall. There's no wall here. On this one, we have no wall. So this is starting off at -infinity. Can I put a right wall? No. It looks like it stops at 4. But again, where is this arrow going? It's going up. I don't care about up though. Remember, domain is left to right. So yes, our eyes naturally go up, but what other direction are our eyes going? Yes, they're also going to the right because this arrow is also going to the right. Now I'm going to exaggerate that again. But that's what that arrow is also doing. That graph is also going to the right. Yes, going up, but it's also curving to the right. So there is no wall here. Because there is no wall, where do we go to? We also go to infinity. I need every single point, all the real numbers, to make that specific graph. This thing is going every which way, left to right. Negative infinity to positive infinity, which means that, okay? This graph uses every x value in existence. What about the range? What's that? Same thing. On the range, I don't have a floor here, so bottoms up. I always have a few kids want to say, hey, the floor looks like it's right here at -5. Oh, no, no. Or right here at -6. Again, no, no. Now we are thinking about bottom and top. But that arrow, I do care about going down and down and down and down to the second floor, to the first floor, and forever and ever and ever. So this is starting way down here at -infinity. This thing does not have a floor, okay? Because that arrow is pointing down. Okay, as I go bottoms up, started way down here, up, and I don't have a ceiling. Because we already said this goes to the right, and this also goes up. So does it have a ceiling? I need every x value, and we also need every y value to make this specific graph right there. Okay, so we say -infinity to infinity off of that one as well. Okay, it's because those arrows are going like that for both of those. Okay, all right, let's go to the next one. We got a partial quadratic here. Okay, domain, left to right, and our domain from left to right. Do I have a left wall?
No.
Here on this one, we can see that it is clearly terminating at -3, isn't it? Again, x is for the domain. Can I put a right wall in there? We can see it's clearly terminating at 2. Brackets and parentheses. Bracket and what? Parentheses. Cool. Y's for the range. Bottoms up, people. Can I put a floor? The bottommost y value, it terminated right there, is at -5. Keep going up, 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 so I make a ceiling. Yep, it does stop. We can clearly see it stops at 4. That's what we call our vertex. Excuse me, which is at 4. Brackets and parentheses. What do we got? -5 is a. Yep, we can see that's closed to be a bracket. And what's 4 going to be? They're both solid. Just because up there there's no like point like there is there. Oh, there's a point there. It's just a solid point. Okay. If we can do those, you're completely on the right track. Okay. Now the last one we're going to talk about here. Let's do the domain. The range has a small twist on it. On the domain, left to right, can I put a wall up on the left? Yeah, my arrows are pointing to the right, not to the left. So I do have a wall on the left, which starts at 1. But now on the right side, I can't put that 5 up there, can I? So both of these telling me they're going past that wall and going towards which direction? Infinity. What do we got? Parentheses or brackets? Parenthesis, parenthesis. Sounds good. Now, I said watch the range on this one. All right. Bottoms up. Do I have a floor here? No, this thing does this. So no floor. When we have no floor, that means we're starting where? -infinity. Okay, up, 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 and right here is where we're going to watch out for. What happens here at that open hole? So it's like I'm sliding my shoes along the ground. I pick my shoes up and I have to step over that. There's a hole there, isn't there? There's a hole in my graph. that next year. Okay. There's a hole there. I got to step over it and it keeps sliding around. It continues on, right? So when I stepped over that, where did I step over that at? What y value? 2, right? So we get a pause at 2, right? So tell me what happened just now. Parentheses and brackets. Negative infinity is a, now that 2 is a what? It's open. Open is a parentheses. I stepped over that hole, and then I continued on, right? So what we then do is we call this the union symbol. We're going to join it with where we picked up at. Where did I pick it back up at? So I picked it back up at 2. I'll talk about it in a sec. And then what do we do? Yep, infinity goes. So here's the thing. By us saying parentheses both at 2, that means everything works for us. Everything works for us except what value does not work? 2. By using parentheses, parentheses not inclusive. 2 does not work. 1.99 does. 2.000001 does. But 2 does not. That's what that's saying there. Okay? So it's like, oh, there's a dog poop. I stepped over it, and I'm working on it. Bringing those get dogs. All right? Stepped over it, and I'm moving on. That's what that means. That's that union symbol. It joins those 2 ranges together, but you skipped over that 2. Okay? Everything else is good to go. All right. I think that's probably where, yeah, that's where we're going to pause it. So that's our first day of whatchamacallit?